started the functional independence and normalization problem. Before that, I think that you already passed for the due of the quiz regarding to the index. No, it's not yet. So I think that you probably have the last I'm not sure, the quiz, the online quiz on Canvas regarding to the index. No, I will check it anyway. If not, I will assign. Okay, so please try to understand. Please do yourself. Okay. Even though you can understand what is a B3, what is a B plus 3, but you can quickly forget or sometimes hard to apply your idea to build the construct B3 and B plus 3. So I strongly suggest to you draw the node structure node by node and erase, draw, and again, then finally you can understand that. Today we are going to continue about the normalization. So there are, as we discussed before, two ways of the designing the database system. One is we can follow the traditional way, conceptual design, and the logical design, the high-level design, then the physical design, or the low-level design. Okay, so that is from the ER modeling. Then we can convert into the relational schema. Then such a relational database schema easily convert to the SQL. Then we can create the database. That's what you have done so far. However, sometimes if the database size is not that big, we can start from the one big jar. So we can put all the information into the jar. Then it's one of bag. So one big bag. Then we can classify by the meaning or the sum. At that time, what we need to consider when we design such a database is, though we don't want any redundant information. So that's actually our goal to when we design the database. So in other words, if we have the redundant information or duplicate data, it's very hard to manage. Also, it's very hard to search the data. So that's our goal. Based on that idea, we are going to talk about the normalization process. So normalization eventually will be used for two ways. One is you can use the normalization process for your designing database. That's actually what you are doing in the classroom project. If you already took the the programming course, some of you guys already used the SQL Server. At that time, did you follow the traditional step like the ER model or the whatever? You can just create. How? Because it's small. So you can put all the information that I need, like I need the customer information, employee information, department information. I can classify easily, and also easily recognize which data is duplicated or redundant, and then. So we can borrow such an idea when we design the database using the normalization. That's one way to use such a normalization that we are going to discuss. Another way is after we build a very big database design, like for example, when I joined the first project as a database administrator, it's almost 20 years ago. At the time, I entered my project manager room. His room is not bigger than my office at the technology building, but all three sides actually covered by ER diagram. So he printed out the entire ER diagram. He said, do you know how many entities are here? He said it's more than 2,000 entities. It can be easily 3,000, 4,000 tables. So can you do such a database, a huge database design using such a one bag? No, it's not impossible. Also, even though you follow the ER model and the relational database schema and the SQL, still sometimes you cannot find some duplicate or redundant information. So how can we judge? How can we find such a problem on our database design? Okay. In other words, is there any goodness measure? Is there any measurement to judge whether my database design is good or not? If not, we can enhance, right? So at that time, we can use such a normalization process to judge our database design. So how can we judge the quality of the database design? Okay. thing is the semantic. Semantic means the meaning of our design should be very clear. Employee is an employee, everybody can understand. So we can put only employee information. But if we are saying just a person, if we define the person entity in the universe database, we have so many different persons. So to address that problem, we can use the super and subclasses, something like that. So it should be very clear. Also, as I focus on the emphasize on a lot, it should be redundant information. But frankly speaking, no, redundant free database is not possible. Okay? Usually, there exists any redundant information semantically or structured. So, but we'd like to reduce such a redundant information as much as possible. Also, null value, reducing the null value. What is a null? Null is another characteristic of the relational database model. What is the null? Null, nothing. Nothing. Why we need such a null data? Null is nothing, then why don't you ignore such a data? But we consider null. We are using null data structure for nothing. Nothing we can ignore, right? But we need to consider, we cannot ignore such a null data. Why? It's because of the definition of relation. What is a relation? Why don't we go back? The definition of the relation. Relation means a set of tuple, rows, and also set of column. So we have the one data for Lee and 111 and 57 Tower Drive, and also another tuple. This another tuple should have the same column, same format, same data structure, but so James. So 222, but do not have the address. If we do not consider without null, it cannot be part of this relation. We need to make the same data structure, but sometimes we do not have the data. Okay, so we need to have something new data structure that is null. However, null does not mean nothing in terms of data structure. You need to do something like at least 1 byte of data to represent the null, right? It's a waste of space. If you have too much null data, you may lose meaning of the data, right? So all of them are null except the primary. So I have only the James. What is a James? It's a student, it's an employee, it's a person, we don't know, right? So we try to reduce as less null as possible. That is better. But as we have seen before, it's not easy, it's not possible. Null-free database design, right? So as less null as possible. Also, sometimes when we operate something, the relational operation, including the referential integrity or join operation, if your design is not so good, it may produce superior tuple, which means unexpected data will be created. We will see details, the example of superior tuple. So that is as less the no possibility of such unexpected. That is the measurement of the quality. So our goal is the clear semantic and the less redundant, the less null, and no superior data. That's our goal. So we are going to discuss about the such normalization process in 2 ways. First approach is informal way. Okay. Second approach is formal way. Informal means not normal, not formal. Then formal means equation. So informal way means without using mathematical notation, equation. I'm going to explain. I already did it here. So what is a good database design in terms of a relational model? Each table, each entity should have how many semantics? how as much as you can. So for example, student table represent only student information. What if student table include instructor information? What if? What do you think? So you design the student table, okay? So for example, this is a student table. So I'd like to add instructor information. So who is the instructor? Professor Lee. Okay? And this student also has the Professor Lee as the instructor. Already duplicate redundant information. What if I change my last name? Please, you need to change all of them. That's the problem. So first guideline when you design the database, the first guideline is one table, one meaning. Okay, that makes sense. That's what you did in your programming class. Because of that, the simplicity, you actually did your database design. So it's a very simple idea. So first guideline is each relation should have only one, the mean. Relationship, one meaning. Otherwise, it can be redundant information. It may have a lot of null data. Okay, that violate in terms of the quality of the measurement. So it's not a good database design. It's a simple. Okay. So for example, the employee, yes, and department, yes. Department, location, project, workshop, each one has their own meaning. Okay, that is the first guideline. So even though you do not know much about the database design, when you see the database, or when you create the database, create one table for one meaning. That's it. In case of the simple, relatively small database, you can do that. So next one. The next guideline is the anomaly. So anomaly means, so let me give the example of such an anomaly. So I think I have the example. Oh, let's use this example. So this is the initial design of the database for the company. I create the employee underbar project relation or table. It includes the employee number, project number, E-name, and P-name, and number of hours. Using even first guideline, is it good design or bad design? It's a good example or bad example using first guideline. What is the first guideline? One meaning for one table. How many meaning can you find? Even actually 2 or 3. Employee information, project information, also number of hours information. It's too many information. So that's okay. Just ignore them. Then let's see. At this time, why don't you change the project name here? Okay. So project name P1. Project name is the P1's. Project name is the project A. We change the project A into project 1. How many data do you need to update? Just one? Why don't you see? Employee 111 in P1, 112 P1, 113 P1. Same thing, same thing. You need to update as number, how much? The number of the employee who belongs to P1. That's not a good. We just change it one project, but you need to change many data. Why? This one is happening. Because of the redundancy. Okay? That's called the update anomaly. Actually, we expect to update one data, one project, but we need to update many tuples. So that is called the update anomaly. It's the same thing for the deletion. I'd like to delete the, for example, in this. So we have, fortunately, the only one data. project 1 has only one employee. Okay, it's okay. Then if the 111 retire or the fire, so we delete this data. Delete the file, the tuple from this table. What's the problem? Where does the project A go? Where's the project A? It's deleted, right? I don't expect to remove the department, but department was deleted because of the employee. Okay? That is called deletion anomaly. I don't expect to remove the entire department, but because of the bad database design, okay, you can. Okay. What about the insert? When you insert the data, I have a new employee. Okay, new employee is not assigned to any department. Can you insert the data in this? You should have the project. Okay, first thing you need to assign the employee, new employee to any project. Okay, this really happened in the real example. At that time, one of there's a workaround, several ways of the workaround. For example, you can have some default project number. At the project number 0. Okay, it's default. Or you can assign any project first. So that is still anomaly. So that's called insertion anomaly. So delete anomaly, the insert anomaly, update anomaly. Why? Why? What caused that problem? Why you got such a problem? Because design. Your database is not well designed. Solution? You need to address that problem. We will see what can be the solution. Solution is very simple. In this design, database design, very simple. You know that?
Normalization.
No relationship?
Normalization.
Normalization. What does it mean, normalization? In other words? General. Why don't you keep your mind? You don't have to worry about whether you or not you understand. Segmentation. Okay, why don't you keep it? Keep your mind. We will see what is a segmentation. Answer is always segmentation. You know what is a segmentation? Chunk. Okay? So grouping. So segmentation is the only solution that works. So we will see how. So we have such an insert anomaly, delete anomaly, update anomaly. Why? Because our database is not well designed. Okay? This is an example of that. Okay? So you can see that we have two different employee and the department information in one table, and or sometimes three different information. So we need to address that problem. How? Segmentation. How we can segment? We will see later. So this is another example of that. Because we have the redundant information, when we delete, update, insert, it will be the big problem. Okay. So second guideline is no anomaly when we are doing the database operation. Okay. Third one is also very simple. We already discussed about the measurement of the quality of the database design as less null as possible. Same thing, we try to have the more null data, no, if possible, as less null as possible. Not only because the null is not the general, the data structure, but it can consume waste of the space. Okay, you need to certain the physical data structure to represent the null data. Okay. The first guideline, one meaning, one table. Second guideline, no anomalies. Third guideline, as less null as possible. The next one is no spurious the tuple when you operate, when you are doing the database operation. So what is spurious the tuple? For example, why don't we check this one? We'd like to join two tables. One is the employee underbar location. Another, we don't care the first, second, third guideline. Okay, so even this is not good for based on the first guideline, right? we have employee information, location information, employee information, project information, something like that. But suppose that this is the initial, the database design. So we have the employee underbar location, these are the data. And we have another employee underbar project 1. Okay? What if we apply natural join between two tables? What is a natural join? Same column name.
Location.
So we have P location and we have P location. So join operation consists of what? First, this. What is that? Cartesian product. What is the Cartesian product? This, all of this. The next, this, all of this. All the combination. Then apply condition, selection operation, right? Selection condition. In this case, selection condition is P location is equal to P location. So for example, the this tuple value is this one. Also, this oops, last night I practiced. There might be option of erasing using this button, but I still need the time. So, so this value, John B. Smith value will be joined with what? As long as it has the same location, it will be joined. This and this. And two of them. So we can join John B. Smith with this one and this one. What about the social security number of the John B. Smith? Does he have the two social security number? No, definitely one of them. Right? However, when we natural join the two tables, it will produce two different John B. Smith. Why this one is happy? Because your database design is not good. Okay? Something problem. It has a P location here, it has P location here, it's a mixture. Okay? So it's supposed to be only one. But this one will be. What about the another? Here. Another value will be created here. Because here, this is called the superior tuple. Okay? Why? Because your database is not a good design. So we need to address that problem. Solution? Segmentation. You don't have to worry about right now what is a segmentation. So will be, you will understand the later. Okay? So this the stuff is the superior tuple. So because it is not a good database design. This is the informal guideline when you design the database or when you judge the database, initial database design. It's so simple. But what is the problem of the informal way? Informal way is easy to understand. Everybody can understand the full guideline. So if we can apply, practically it cannot cover each and every cases. In small case and special case, you can easily apply such a guideline, but huge size of the database design, not easy. Okay? It's not general solution. So the next is, so we are going to discuss, we are going to learn the formal definition of the such a normalization. Okay? Which is based on functional dependency. What is a function? When is the first time you learned about the function? Algebra. High school? Junior high school? No, I don't think so. Even the elementary school you learn. Whether or not you realize. So, when I learned the function first time, I learned it this way. So my math teacher, it's not homeroom teacher at the time, gave me this example. This is the kind of black box. It's a box. Actually, in Chinese, the function means it's the box, right? I'm not sure.
No.
Any Chinese student? No? Really? At the time you can say yes. Okay, so inside the box is usually times 2. I will learn the Hindi next time. So it's a times 2. If the input is 1, output is 2, and input is 10, output is 20. Right? If input is x, output is 2x. So when we say the input is x, large x, output is a large y, we can say that this function f is equal to y. So y equal 2x, so y equal 2x. This is a function, right? It's algebra. I should be the math teacher. It's easy to understand, right? So that is one of the natural process when you study the math. Even though you cannot understand right now something algorithm or math, you may realize a year later, even though I didn't study for that part, you understand. That's the usually happen when you study math. Why? Practice. Practice? No. Math is not like the other subject. Math is kind of this step up. So without understanding this one, you cannot understand the next level. In other words, if you understand the next level, automatically you understand the behind. That's true. So that's the reason sometimes you don't have to stick on, you don't have to spend a lot of time, the algebra 1. You can keep going. When you understand the algebra 1, even though you do not understand the algebra 2, you understand algebra 1. You may realize that. That's true. So without the definition of the function, you cannot understand calculus. But when you understand the calculus, the function logarithm and the trigonometry is easy to understand. So anyway, this is a function. Why am I showing the function here? What is the most hateful thing for the administrator in database? Redundancy. So how can you formalize such a redundancy?
Using functions.
Using function. What about this one? 20, y is determined by x. Right? So if we know the y, if we know the x, then we know y is automatically determined by the function f. Similarly, in the database design, if we know the primary key, for example, social security number 1, 2, 3, 4, 5, 6, and 9, we know the other attribute. So we can apply such a function to the database design if we define x and y as the set of attribute. A set of attribute x determine set of attribute y. For example, if I know the UBID, I can find name, major, GPA, all other attributes. That makes sense. That's how usually. You can say it. You don't have to just point. Okay? I still don't figure out why sometimes it's the dot, sometimes next page. So if we know the x, it determines y. So what about the relation? How can we interpret this one? It's a kind of dependency. So how many dependency do we need in one table? Only one. In other words, if we can find many dependency, many function, then that is the problem that violate the first guideline. Right? At that time, this is called functional dependency. It's the same as the concept of function. It's a set of attribute, set of attribute. So, but it is true. How many functional dependency can you find from the real example? So, for example, in this employee underbar department, how many functional dependency can you find? One. For example, let's see.
2, 3, 4, 5, 6,
social security number determine what?
Every other one.
E-name. Okay? That makes sense. What's the social security number determine? B-date.
Every other one.
What's the social security number determine? E-name plus B-date. And also, social security number, comma, E-name determine B-date. That also possible. How many? Only 4? I can make as many as possible.
So many.
It's a all combination.
Yeah.
Actually, how many functional dependency? So many dependencies. So we cannot say only one dependency in the table. There exists so many dependencies. However, we don't need this kind of thing, right? Only, how can I say, core dependency, non-additional information, which means social security number, social security number determine E-name, comma, B-date, comma, address, comma, D-number. E-name, B-date, birth date, address, D-number. It cannot determine the D-name. Okay? So only D-number up to D-number. Also, we can find another core dependency. That is D-number determine D-name and D-manager social security number. This is called minimal functional dependency. Actually, minimal functional dependency is mathematically defined. Okay? The minimal set of functional dependency. This is the functional dependency and the minimal functional dependency in case there is this is one of the mathematical way to define the minimal. Minimal means if we take out one of the attributes that will be different from the original one. That's usually the one of the way to prove the theorem or equation or define such a minimal. Because it's a minimal. From the minimal, if I take out something no additional information, that will change the meaning of that functional dependency. So that is the minimal dependency. What about the just general dependency? So for example, social security number, E-name. If I take out the E-name, still it's the same dependency, right? However, from the SSN, if I take out SSN, there's no functional dependency. We cannot take out. So that is the minimal dependency, but I'm not going to discuss in the using formal way about the minimal functional dependency. I believe intuitively you can understand what is the minimal functional dependency. So our goal is to find not just general functional dependency, minimal functional dependency. Then how many, let's change my question. How many minimal functional dependency do we need for good database design?
A table.
Per table?
One.
One. Then that makes sense. One meaning, the meaning means one minimal functional dependency. So our goal is to find minimal functional dependency. So there are a lot of the mathematical approach to define such a thing. So actually such a functional dependency has such an inference rule. Inference rule you have learned in set theory in your algebra course. So reflexive means if y is a subset of x, definitely x determines y because y is a subset of x. Like the social security number, comma, the name. The name is determined by the social security number, such like augmentation, transitive. if x determine y, y determines z. X determine y and y determines z. That means x determine z. That's the transitive that I think that you can understand easily. There are a lot, several more, the operation, the rules actually. Decomposition is x determine y and z. Then x determine y, x determine z. For example, social security number determine birthday and address. That means social security number determine birthday, social security number determine address. Simple, the inference rule. But we can use such an inference rule to prove such a functional dependency. That is eventually going to the normalization. Then I'm going to skip the closure and equivalent. Then there is a formal way to how to find the minimal functional dependency. Mathematical way. It's not very common. It's not rocket science, but it's not easy to understand intuitively. Unlike the definition of the minimal functional dependency. So I'm going to skip because I try to explain and let students understand. And even in the final exam, I gave this question. Even sometimes the student forget everything, entire the functional dependency. Okay, so I'm going to skip. But if you are interested in the mathematical way of such a database algorithm, you can try to understand using the textbook as well as the PPT file. But idea is, I try to give the idea how we can find the functional dependency. Idea is, first we try to take out the one attribute from the functional dependency. See whether change it or not. If not change it, you don't need that information. Until dependency is the change it, we can take out. Then we can have the only quad, the functional dependency. So right hand side is the usually single. Then when we represent such a functional dependent, minimal functional dependency, intuitively we can keep the left hand side core, right hand side all together. Okay, such a way. So that's pretty much enough to understand the normalization layer. Any question? So how many functional dependency can you find? Yeah. Many minimal functional dependency. In this case, 1, 2. Okay. Then what about this one? Social security number determine e-name. It's the employee information. Then P number determine P-name and P-location is project information. Social security number, P number determine hours is a work zone. Right? 3. Minimal functional dependency. Are they good example of the database design? Good or bad? No, because how many meanings? 2 meaning, 3 meaning. How many minimal functional dependencies? 2 and 3. Okay, what will be the solution? I asked segmentation. I think you are getting understand a little bit. Okay, what will be the solution to make the better quality of the database design? You can segment by what? Minimal functional dependency. So from now on, if I'm saying the functional dependency, that means minimal functional dependency. Okay, so. Usually computer science or the developer, they don't want something the long name or whatever. So I try to use functional dependency. When I'm saying the functional dependency, that means minimal functional dependency. So how many functional dependencies? Nicely draw such a minimal functional dependency, FD1, FD2, FD3. So using that functional dependency, we can make better quality of the database design. How? Segment. We can segment by this functional dependency. That is called normalization process. Okay, that is normalized. But there's a step by step that we will see. sometimes I try to give the functional dependency, minimal functional dependency, for you to make the given database design better, normalization. But sometimes I do not give the minimal functional dependency. If you can find it intuitively, okay, there's such a functional dependency from the data. Okay, mostly I try to give the simple example in the exam, but in real life case, it's not easy sometimes to find such a full functional dependency from the NASA, the database system. No, at that time you can apply conceptual design, physical design, and SQL. Then see, apply such a functional dependency for suspicious one. Let's see whether there exists a functional dependency or not. If we exist, we will see the solution. Okay? So that is the normalization. Okay? This is the normalization. So normalization means what? Segmentation. Solution. If we segment, we can get rid of what? Redundant information. So that's our enemy. Our enemy is redundant information. If there exists a redundant information, we remove. How to remove? Segment. How can we remove? By using functional dependency. So if you do not find the functional dependency, it doesn't make sense. But somebody may be curious. I did the database design without learning this one in my programming class. Then, am I genius? Yes, you are genius, maybe. But the good news is, if you believe you are a normal person with a general education, everybody can do certain level of normalization. That is the third normalization form, even without understanding such a complicated theory. Okay? Even such a third normalization form cover most of the database design in anywhere. Almost 95, 98% of the database design can be done by third normalization form. Which means you don't have to study this because you are normal. But the problem is the other 2 or 5%, okay, which is not the address, right? The general thinking, okay. That time you need to apply the normalization process. So we will see how can we do that. So normalization means it's a process decomposing, segmenting, unsatisfactory bad. We already discussed about what is a bad. It's a redundant information. In other words, multiple minimal functional dependency. How? Segment, breaking up their attribute, okay, to smaller relation. So normal form is a certain condition using key and functional dependency. So we are going to use the key and functional dependency. There is one more definition you need to keep your mind. One is what is a functional dependency? X determine Y, right? It's a minimal functional dependency. Minimal at that time, X is called prime attribute, usually key attribute, either candidate key or primary key. It's a key attribute. So prime attribute. That means Y means non-prime. So non-prime attribute, not candidate key, not primary key. Candidate key also can determine other attributes. It's almost the same unit. It's almost the same as a primary key, right? Candidate key. What's the difference?
Primary key is choose.
It's just selected. So as a designer, you need to select only one primary key from many candidates. Anyone can be the key, but you select this one by considering the application analysis, by considering the situation. Like for example, I have key of for the student, for the employee, I have the social security number as a key, and the UBID, the employee ID as a key. I have two keys, okay? What are you going to select? Which one will be selected for your company database? Employee ID, okay? However, if your system is for taxpayer, you'd better select social security. Okay, it depends. But they are almost the same, so such a attribute will be prime attribute. So normalization process will use prime attribute and this functional dependency. We will see how can we do that. There are step by step. First, second, third, BCNF first. You can understand this way. This is a back of the information. You collect at the beginning of this class I mentioned one way to design the database is you collect all the information in the back. Okay? This is the back. This is called unnormalization form. Okay? It's unnormalized. So there are a lot of duplicate information, everything. So several the functional dependency and the several meaning anomaly and everything. So then apply normalization form. That is the first normalization form. First NF. First NF. By decomposing, by segmenting. We don't know yet what is that. We will see one by one. So let's give. Then we apply another rule, that is the second normalization. Another third. So you can see the relationship. Unnormalization form include first normalization form. First normalization form include the second. Second include the third. That means if you have the third normalization form, that's already first and second. Okay? So usually we are going to start from the unnormalization form, then apply the rule, segment, then make the third normalization form. Then another one is the inside the third normalization form is a BCNF. How decompose? How are we going to decompose? At that time we will use prime attribute as well as the functional dependency. So let's see the first one. To do that, we are going to define the key a little bit more details. Okay? So we know what is a key. Okay? The super key means any set of keys that can define the other. Okay? Among the minimal super key is the key. Okay, so then you understand the key is what? The key that you understand. The super key means any set of the key, like the social security number plus address, can determine other, as we have seen before, right? So that is the super key. But we don't need such a super key in our normalization process. We need a key. Among them, each key can be candidate key. One of the candidate key will be selected as the primary key. So the clear. At that time, prime attribute means left-hand side. That means all attribute belongs to primary key or candidate key. That is the prime attribute. The others are non-prime attribute. So finally, first normal form. First normal form from unnormalization form. Who will check attribute by attribute? Attribute column by column. No composite. What is a composite? Address, like that. The street number plus street name and street type, CD name. What else? The state name and the zip code. So can you remember this one? Address. This is a composite. Normalization form does not allow. I will give this one to you. The normalization form, the relational model does not allow such a composite. Do you remember that when we map the ER modeling to relational model, how did you guys handle the composite key? We can create one attribute, one column for each this one. That's the same. Okay? Why? This is important. Why? Why? We are using relational database model. Relational database model allow
One column at a time.
only one value for column. Single value. Only single value. Only atomic value. So, relational model cannot address this one. It's a very easy concept if you are using object-oriented concept or hierarchical concept. But relational model cannot. So, relational database model does not allow comparison. Same reason. Multi-value? No. What is a multi-value? You remember this color,
Two value.
2 values, 3 values, okay? Many values. What about the relational model? So what about the mapping ER model to relational database model? We create a separate relation table. Why? Somebody should have asked,